What we're going to do in this video is think about functions in a slightly more dynamic way. As we have said before, we can think of a function as a machine. It takes an input, processes it, and produces a single output. But what happens when we chain these machines together, meaning an input of a function becoming another function? That is exactly what a composite function is. It's what we get when the output of one function machine becomes the raw material for the next. We represent this using the notation here, which we read as f composed with g of x. This is just another way of writing f of g of x. Let's make sure we're following this properly. The order here is crucial. We always work from the inside out, meaning the function g is applied first, and its result is then dropped into the function f. Let's see an example. Here we have two functions expressed in set notation, as shown. First, let's find f composed with g of x, or f of g of x. To do this, we first determine the value of g of x for each input x using the ordered pairs. Then we check whether the output of g of x is included among the input values, or x values, of f. If the output of g of x is an input value of f, we can apply f to that value. The resulting output will be the value of f of g of x. However, if the output of g of x is not included among the input values of f, then f of g of x is undefined for that particular value of x. Alright, now let's determine the values of f of g of x. We begin with the first input value of g, which is 1. To find f of g of 1, we first determine g of 1. From the given set, we have g of 1 equals 2. Next, we substitute 2, which is g of 1, into f. Therefore, f of g of 1 equals f of 2. Since f of 2 equals 3, we get f of g of 1 equals 3. Therefore, the ordered pair 1, 3 is included in f composed with g. Now, let's move to the next input, which is 2. F composed with g of 2 is equal to f of 4, since g of 2 is 4, and f of 4 is 5, which is f of g of 2. Therefore, the ordered pair 2, 5 is included in f composed with g. Next, let's find f of g of 3. F of g of 3 is f of 6, since g of 3 is 6. However, f of 6 is not defined in the given set representing f here. Therefore, we say f of g of 3 is undefined. The same applies to f of g of 5. Since g of 5 equals 10, we have f of g of 5 equals f of 10. However, f of 10 is not defined. Therefore, f of g of 5 is also undefined. Hence, the composite function f composed with g of x is represented by the set 1, 3, 2, 5. Now, what about g of f of x? We will use the same process as before, however, this time we apply f first and then apply g. So we start from the input values of the function f of x. For the first one, we have g of f of 2, which is g of 3, since f of 2 is 3. Then g of 3 is 6, so we put 6 for g of f of 2. Therefore, the ordered pair 2, 6 is included in g of f. For the second one, we have g of f of 4, which is g of 5, since f of 4 is 5. Then g of 5 is 10, so we put 10 for g of f of 4. Therefore, the ordered pair 4, 10 is included in g composed with f. Finally, we have g of f of 12, which is g of 13, since f of 12 is 13. But g of 13 is not defined in the function g of x. Therefore, we say g of f of 12 is undefined. Hence, the composite function g of f of x is represented by the set 2, 6, 4, 10. Let's look at another example in which the functions are expressed in equation form. Suppose f of x equals 2x plus 3 and g of x equals x squared. I encourage you to pause the video now and see if you can calculate f composed with g of 2. Alright, Let's do this together. First, we evaluate the inner function, g of 2. To do that, we substitute 2 into the function g of x. Then we get g of 2 equals 2 squared equals 4. Now we take that 4, which is the value of g of 2, and use it as the input value for f of x. In other words, we substitute 4 for x in the function f of x. Therefore, we get f of 4, which is equal to 2 times 4 plus 3, which is 8 plus 3, resulting 11. So f of g of 2 is equals to 11. Now, let's see whether the order does matter. In other words, is f of g of x the same as g of f of x? Let's check by finding g of f of 2. This time we do f of x first, which is f of 2 equals 2 times 2 plus 3, which is 7. Then we plug 7 into g of x, which is g of 7, which is 7 squared, resulting 49. Since 11 does not equal 49, we can see that function composition is generally not commutative. This means that changing the order of the functions can change the result. Therefore, f of g of x is different from g of f of x. In general, you can think of each function as a machine. The output of the first machine becomes the input of the second machine. If we change the order of the machines, we may get a different result. Here, we evaluated each function one at a time, working from the inside out. But what if we need to evaluate the composite function for several different values, such as f of g of 2, f of g of 5, and f of g of negative 3? Instead of evaluating g of x first, and then evaluating f of x separately for every question, we can determine the composite function, f composed with g, first. Then, we can substitute each required value into the composite function and evaluate it directly. Let's see f of g of 2 for an example. First, we determine the composite function f of g of x by substituting g of x into the input x of the function f of x. When we do that, we get 2 times g of x plus 3. And since g of x is x squared, we get 2 times x squared plus 3. Hence, our composite function, f of g of x, will be 2x squared plus 3. Now, to find f of g of 2, we simply substitute 2 into x of the composite function 2x squared plus 3, which will be 2 times 2 squared plus 3, which is 2 times 4 plus 3. 2 times 4 is 8, so we get 8 plus 3, which is 11. As we can see, we obtained the same value as we did when we evaluated each function separately. For the other required values, such as f of g of 5 and f of g of negative 3, we can simply substitute the given values into the composite function. The composite function g of f of x can also be determined in the same. Let's find g of f of 2 and check whether we get the value of 49 as we did before. First, we substitute f of x, which is 2x plus 3, into g of x, and we get 2x plus 3 in parentheses squared. Remember, here we are squaring the entire expression 2x plus 3, not each term independently. So we get 4x squared plus 12x plus 9. So let's substitute 2 into x. So we get 4 times 2 squared plus 12 times 2 plus 9, which is 4 times 4 plus 24 plus 9. 4 times 4 is 16, and 24 plus 9 is 33. So 16 plus 33 is 49. Therefore, our result checks out because it is the same value we obtained when we evaluated the functions separately. Now, let's think about the domain of a composite function. Unlike the combination of functions we discussed in our previous video, the domain of a composite function cannot be determined simply by finding the intersection of the domains of the original functions. For a value of x to be included in the domain of the composite function, f composed with g, it must first be included in the domain of g. Then, the output generated by g for that value of x, which is g of x, must also be included in the domain of f. If both of these conditions are satisfied, then we can say that x is included in the domain of the composite function f circle g. In a set builder method, we can define this requirement as follows. For a composite function f of g of x, The domain of f of g of x is the set of all x that is a member of the domain g of x, such that its g of x is a member of the domain of f of x. Let's see how this works using our previous example. Here in our example 1, our function is expressed using set notation. So when we try to determine the domain of f of g of x, the first requirement is that x must be a member of the domain of g of x. As we can see here, the domain of g of x includes the set containing 1, 2, 3, 5. Once we determine the domain of g of x, which is the inner function, we go ahead and check the output of g for each value in its domain. If the output or range value is found in the domain of f of x, which is the outer function, then that input value of g of x, which is x, will also be a member of the domain of f of g of x. However, if the output of g is not included in the domain of f, then that input value will not be included in the domain of the composite function. Let's check each member of the domain of g. For the first member of the domain of g of x equals 1, its g of x value, or g of 1, is 2, and 2 is a member of the domain of f of x, which are the set of 2, 4, and 12. Hence, 1 will be in the domain of f of g of x. The same goes to the second member of the domain of g of x, which is 2, since g of 2 is 4, and 4 is a member of the domain of f of x. Therefore, 4 will be in the domain of the function f of g of x. However, for the remaining members, x equals 3 and x equals 5, since g of 3 and g of 5, which are 6 and 10, are not found in the domain of f of x, as a result, they won't be included in the domain of the function of f of g of x. Therefore, the domain of the function f of g of x will be the set containing 1 and 2. Now, try determining the domain of the composite function g of f using the same process. Comment below if you got the answer. For our second example, both functions, which are linear and quadratic, have the set of all real numbers as their domains. Therefore, the domain of their composite functions, whether it is f composed with g or g composed with f, are also the set of all real numbers. In this example, both composite functions are quadratic functions, and we know that the domain of a quadratic function is always the set of all real numbers. However, we can't always determine the domain of a composite function simply by looking at its final simplified form. Instead, we must always consider the original functions, because simplification during composition may hide some restrictions on the domain, as we saw in our previous video on the combination of functions. Here is an example. Our f of x is a rational function, whereas g of x is a linear one. When we do a composite function, g of f of x, we insert the function f of x, which is x squared minus 1 over x minus 1, in x of the function g of x. When we do, we get x squared minus 1 over x minus 1 plus 2. When we factorize x squared minus 1, we get x minus 1 times x plus 1, which is over x minus 1 plus 2. When we cancel x minus 1 by x minus 1, we get x plus 1 plus 2, which results x plus 3. The resulting composite function is linear. If we look only at this final simplified equation, we might conclude that its domain is the set of all real numbers, because a linear function is defined for every real number. However, according to the definition of the domain of a composite function, x must first be a member of the domain of the inner function, which is f of x in this case. Yet the original function f of x equals x squared minus 1 over x minus 1 is undefined when x minus 1 equals 0. Therefore, x equals 1 must be excluded from the domain of f, because the denominator cannot be equal to 0. And according to our definition here, an input x first has to be a member of the inner function, which is f of x, in order to be considered for the domain of the composite function. Even though the factor x minus 1 was canceled during simplification, the original function f of x is still undefined at x equals 1. Therefore, 1 must also be excluded from the domain of the composite function g composed with f. Hence, the domain of the composite function is the set of all real number except 1 instead of all real number. Therefore, the simplified equation x plus 3 gives us the rule for the composite function, but it does not show the restriction x being different from 1. This is why we should always consider the domains of the original functions when determining the domain of a composite function. Finally, let's look at a practical example. Here, our word problem says, a stone is dropped into a lake, creating a circular ripple. The ripple travels outward at a speed of 30 centimeters per second. Find the area of the ripple as a function of time, and determine the area of the ripple after 6 seconds. I'll give you a moment to think about the problem and try solving it yourself. Feel free to pause the video. All right, let's solve it together. What we are given is the speed at which the ripple travels outward, which is 30 centimeters per second. When a stone is dropped into a lake, the ripple spreads outward in all directions, forming a circle. Therefore, the distance the ripple travels outward from the point where the stone was dropped represents the radius of the circular ripple. Since the ripple travels outward at a speed of 30 centimeters per second, its radius increases by 30 centimeters every second. So let's say our radius will be r of t, which means radius is a function of time, which is 30t, or 30 centimeters for every time t, where r is measured in centimeter and t is in second. And the area of a circle, a of r, meaning area is a function of radius, which is pi r squared. Here, radius is an input for the area function, but radius is also the output of the function r of t. Since the question asks the function of area in terms of t, or time, we substitute the function r of t into the variable r, or radius, in the area function. So when we do, we get a of r of t is pi times 30t the whole square, and this results area of the ripple is 900 pi times t squared. This is the area of a ripple as a function of time t in second. The second question is the area of the ripple after 6 seconds. To solve this, we just substitute 6 into the area function we found, and this results around 10.18 meters square after dividing it by 10,000 to convert our result into square meter, solved as shown. To wrap everything up, a composite function applies one machine after another, and the order matters. While it isn't commutative, it is associative, meaning f of g of h equals f of g of h. This concept is also the foundation for inverse functions. When a function and its inverse are composed, they undo each other, which is why we say f of f inverse equals x. We'll see this in our coming video, which deals with inverse of a function. And we're done. Hopefully that makes some sense and helps you feel ready to tackle these on your own. If this walkthrough was helpful, hit that subscribe button to keep mastering math with us here at Rimetric Walkthrough. Thanks for watching, and I'll see you in the next video.